this microphone? There it is. Howdy, folks. Look at this audience. They definitely saved the best for second to last today. You guys are in for a treat. My name is Dean Proctor. I'm a Principal Solutions Architect with Couchbase, and I am super psyched to be talking to you guys about performance tuning. It's a topic near and dear to my heart. I could literally talk hours about this and might, so sorry to the timekeepers, but their loss is your gain. This is a very complex topic, and unfortunately it only gave me 45 minutes to speak to you today. So my goal is to sort of pare away some of that complexity and surface the specific subsystems and tunables that matter most in a Couchbase environment, and give you some basic guidance as to how to address those. Before we jump into the tunables, I think it's important to ask the question, why get into this jumbled mess? This is a very dense topic, a very complex topic. And in my opinion, the answer is really threefold. The first is my company spent a lot of money on provisioning resources for Couchbase to run on. I want to make the best use of those resources. Second, as an operator, I want to make sure that my system is highly resilient, and tuning can help with that. And thirdly, I want to attenuate the latency, throughput, and resiliency of my system to match my workload and my requirements. And in a nutshell, that's what tuning is going to do. I think it's also important to recognize what tuning won't do. Tuning is no substitute for improper allocation of resources. If you don't provision your system with sufficient resources for your workload, no amount of tuning is going to get you out of that hole. If you didn't attend Perry Krug's talk on sizing yesterday, I strongly recommend that you take a look at the video once it's posted online. Make sure that your clusters are sized properly out of the gate, and then tune from there. Next, tuning will do nothing to account for a poor data model or improper access patterns. There have been a number of talks about how to properly set up a data model that works well with Couchbase. Definitely take some of those points to heart and incorporate that on the application side. Again, you can tune to your heart's content, but if your data model is just not correct, it's not going to do much for you. And then finally, it's important to recognize that out of the box, Couchbase is already a really fast system. It already buffers a lot of I/O in memory. It already auto-tunes itself in recent additions to the available system resources by allocating threads based on the number of CPUs you have or the amount of disk space you have available. So we can get a lot of gains by tuning Couchbase, but it's not to the same level you would expect in other systems. You're not going to expect a 2 to 4x performance gain by tuning your system running Couchbase. Couchbase already does a lot of that work for you. So caveats aside, let's jump into it. If we, on the operating system side, get into the virtual memory system, which is one of the two systems I want to talk about, virtual memory and storage. If we really simplify it, from a Couchbase point of view, this is what it looks like. We have some allocation of physical memory, RAM. We have some amount of disk space that we can use as swap. If you don't have swap enabled, make sure that you have swap enabled. Within the kernel, we have a swapper process whose job it is to, at some point, move pages out of physical memory and put it on disk, and vice versa, pull it out of disk, put it back in memory. And then we have this OOM killer, stands for out of memory killer, whose job it is to make sure your system doesn't crash in the event that you run out of memory by killing processes that are consuming a lot of it. Our job when we tune is to address how physical memory is being allocated, to do our best to prevent memory from being swapped. Couchbase already has facilities for moving data between memory and disk. Having the system do that for you out from under Couchbase is a bad thing. And finally, try to stave off that OOM killer. We don't want our processes killed. The first set of tunables that we want to address, if you get nothing else from this talk, that first one, VM.swappiness, make sure that that is set to either 0 or 1, depending on your kernel level. What this does is control the propensity of the kernel to want to swap those pages out of memory and put them on disk. Like I said, Couchbase already does this for you, so long as you've allocated sufficient memory to Couchbase, there should be no need to swap, and we don't want the OS doing it for you. If you're running a Linux kernel version of 3.5 or lower, set this value to 0. If you're at 3.5 or higher, set it to 1. the meaning of the variable has changed a little bit as the kernel evolved. But essentially, it does the same thing. It says only swap in order to prevent the system from crashing. Otherwise, don't swap. The other setting with regard to memory allocation that we want to tweak here is the use of transparent huge pages. This was a really good idea put together by some really smart engineers. And the idea there is to decrease the total number of pages in the system by, in the background, combining multiple small page allocations into larger page allocations called huge pages, which could range from 2 megabytes to a gigabyte, with the goal of making the overall memory management system more efficient. In reality, this really smart idea on paper turned out to be a very bad thing for memory-intensive applications because it can cause very long delays for allocating new memory in the system if it has to go and try to reshuffle these pages in the background into larger pages before it can give you a new allocation. Our recommendation is just shut it off. You don't need it. Couchbase can operate just fine without it. There's two ways to do it. You can turn it off in your grub.conf file by adding a transparent huge page equals never parameter to your kernel configuration line. Alternatively, you can disable it by echoing never at runtime into the parameters on screen. And don't worry about taking pictures of the screen. All of this will be available on the website after we're done. The next really smart idea that we want to talk about is NUMA. And the idea behind NUMA, NUMA stands for non-uniform memory allocation, is we can get lower latency access to memory, we as being consumers of hardware, if CPU sockets are directly connected to certain banks of memory. Really smart idea, but in order for it to work, the hardware has to support it, the OS has to be aware of it, and the application also has to be aware of it. Couchbase, like many other database systems, isn't NUMA aware. And when that happens, you get some weird effects. So in the operating system layer, what NUMA looks like is these collections of nodes. A node is a CPU socket and its associated memory banks. So if a thread is running on CPU socket 1 and it wants to allocate some memory, a NUMA-aware OS is going to allocate that memory within node 0. If a thread is running on CPU socket 2, that memory will be allocated within node 1. Now, if you have very memory-intensive threads all running on node 0, say there's an imbalance in how those threads are distributed between your sockets, you could end up in a situation where you consume all of the memory in node 0, and your system actually starts swapping, even though there's plenty of free memory available in node 1. Very weird thing to happen. Alternatively, because these threads do switch between processors, you could end up in a situation where you have a lot of memory allocated in node 0, but all the threads that want to access it are running on node 1, which means all of that access is going over this QPI link. Stands for Quick Path Interconnect. Think of it as the connecting bus between the NUMA nodes, in which case you could see very weird latency spikes as these threads move around. Again, really smart idea. It's not supported with Couchbase, so it's really just best to turn it off. And again, there's two ways to do it. First is disable it in BIOS. It's the recommended way. Otherwise, you can disable it at runtime. You would need to install a utility called NumaCTL. It's all of your package managers would support it. And in your init script, you'll find a daemon variable in the startup command. You just prepend that with NumaCTL -- interleave all. And what that will do is just inform the OS to round robin the memory allocations between all your NUMA nodes and prevent that imbalance in memory allocation. You'll also need to set zone reclaim mode equal to 0 if NUMA is still enabled in the OS. All right, moving on to storage. And by the way, I clocked myself doing this talk this morning, and I came in about an hour 20. So we're going to have to keep up this fast pace. I'm happy to answer any questions if you guys want some detail after the talk. Linux storage architecture. At a very high level, this is what it looks like. We have a virtual file system layer. Under that, we have a caching layer. Not exactly correct, but for our purposes, that's pretty much the way it works. Under that, we have a block layer, and then below that, we finally get down to the physical tier, which is your disk or your storage controller. Within each of these tiers, there are a number of tunables that we can work with. So in the file system layer, obviously we can choose which file system we want to deploy Couchbase on top of. We can change the mount options for how those file systems act. Within the caching tier, we can control how we're allocating memory within the page cache or the inode cache or the dentry cache. We can also affect how frequently that cache is being flushed. At the block layer, most importantly, we can choose our scheduler algorithm, which determines how that cached memory actually makes its way on the disk. And we can control the depth of the I/O request queue. And we'll talk about how that's important. And then finally, at the physical layer, we can choose the type of physical media we deploy upon, the allocation of that physical media, and of course, if you're using RAID, some of the options that are available there for tweaking. We start in the virtual file system layer. Two options for file systems that I see most commonly deployed. They're good options. The default in most Linux systems will be ext4. It's a pretty decent option for Couchbase. The alternative, which is my favorite, is XFS, and that's largely because it's slightly better for append-only workloads, which Couchbase is largely. But either one is going to be a fine option. As far as mount options, a few items here. Regardless of your file system, turn off A-time via that no A-time parameter. A-time stands for access time, and it's generally regarded as the worst idea to make its way into Linux kernel. Couchbase doesn't require A-time. In fact, no real applications other than mail servers maybe actually use it anymore. Even if the operating system defaults to rel A-time now, Couchbase doesn't require any time. Just shut it off. It'll make your system overall a little bit more efficient. The next option is barriers. Barriers control essentially the ordering of writes to disk. And if you have a battery-backed storage controller, it is considered safe to disable barriers at mount time. And this is actually a really big performance boost for disk I/O. If you don't have a battery-backed storage controller, don't disable it. You could end up corrupting your disk or corrupting your file system. And that same thing applies to the data equals write back parameter. You can get some decent performance gains for disk I/O by adding that parameter. Again, this has to do with the ordering of writes to disk. This is generally considered always unsafe, though. If you do choose to use this because you need those disk I/O gains, you'll want to make sure that you are using replicate2 for your writes to make sure that you have multiple copies of your data. And you'll also want to make sure that when you do recovery, you're not using delta node recovery, you're using a full recovery. Any data that resides on a server that hard crashes when you apply this particular parameter should be considered corrupt and unsafe.
Do you have any special mounting for the SSD?
I don't. There aren't really any parameters that I've seen that have made a big difference, at least in my testing.
So what are loader ACAP?
What's that?
There is a loader ACAP?
I'm not familiar with it. I do have a lot of material. Happy to answer questions, but let's hold them to the end. As far as XFS, a couple of additional parameters there you can set. These largely have to do with the binary logs that XFS is dealing with. So generally, we're increasing the number of log buffers, increasing the size of them, and also increasing the default allocation size for new objects just to prevent fragmentation on the file system. Those really aren't going to affect performance too much, just general best practices when you're working with XFS. For the page cache, now this is moving down to the caching layer on disk, and this is essentially what's largely buffering your disk I/O outside of Couchbase. A few settings that you want to work with. The default defines the amount of dirty bytes that the cache will be allowed to keep. The default setting in Linux is to keep or to allocate up to 20% of your overall system memory to the caching of dirty writes, which might have made sense 15 years ago when that setting was introduced. But now that you can have several, 100 gigs of memory in a single system, Trying to flush multiple gigs of data all at once to disk is a great way to essentially DOS your disk. You're going to quickly consume all of that available disk I/O. My recommendation is to reset that, limit the amount of dirty bytes that can exist in memory by lowering the parameters of your VM.dirtybytes setting. Again, this is a sysctl. I recommend something around 200 megs to start. And as you're testing, you can try tuning that up. What you're going to want to test is when you're taking a look at your disk I/O, what you want to avoid is a sawtooth pattern, right? Where you flush, and then you're buffering, and then you flush, and then you're buffering. What you're going for is more of a flat curve. So start at 200 megs, and then ramp up until you stop seeing the flat curve. The dirty background bytes in general should be about half of whatever you set your dirty bytes to. So if you set dirty bytes to 200 megs, set dirty background bytes to about 100. Next set of parameters control how frequently the system looks for dirty blocks that need to be flushed to disk. Two parameters control that. You have the dirty expire centisects, which defines how long a dirty block can exist in memory before it's forced to be flushed to disk. And then you have dirty write back centisects, which controls how often the flusher wakes up to check. By default, dirty expire centisects is set to 30 seconds, which is just a huge amount of time for a dirty block to exist in memory. I recommend that you back that way down to something like 5 seconds. If you're on a very low bandwidth network-based file system like EBS, God forbid, in Amazon, you might want to back that down even further to something like 3 seconds. And then for dirty write back centisects, back that down from the default of 5 seconds to something more like 1 second. And finally, for page cache, there is an additional parameter called VFS cache pressure. This is another sysctl tunable. What this does is control the propensity of the operating system to flush inode and dentry caches in favor of page cache. What those are doesn't matter. It's another way of buffering disk I/O. If you have a lot of free memory that isn't being consumed by Couchbase, then you can, but you are experiencing a lot of disk I/O, you can try backing this parameter down, decreasing it from its default, and that will instruct the OS to allow more memory to be allocated to those particular caches. And in general, you should see an improvement in I/O. Scheduler. The scheduler is huge. You can see really big performance gains by tweaking these parameters. The scheduler algorithm determines the algorithm for how these dirty bytes actually make their way onto disk. The default is a scheduler algorithm called CFQ. It's really what I consider a desktop quality scheduler. It's meant for a system where you're running many different applications and you want to fairly allocate disk I/O to all those applications. That's not relevant to Couchbase. A much better option is the deadline scheduler, which essentially is a FIFO, but it does basic reordering and merging within the scheduler queue and guarantees a maximum latency for any given write that's in its queue. Another option that is also potentially good but less frequently used would be NoOp. If you're running a high-end storage controller that has its own scheduler, sometimes reordering your writes in the operating system can be redundant, and you might as well just pass it on to the storage controller. But very often, these storage controllers can benefit from having a pre-ordered set of writes. So my recommendation is just default to deadline. And then finally, the I/O request queue. Now, this is where you get a lot of your performance gains. This is the queue that determines how many objects can be essentially reordered prior to them being flushed to disk. The longer the queue, the better your ordering of writes and the fewer head movements your spinny disk is going to encounter when you start actually writing all of this out the disk. Essentially, you'll get better throughput with the longer the queue. The trade-off here is longer the queue, the greater the latency. So I found a good Goldilocks number for the scheduler request queue is around 1,024. The default's 128, that's way too short. 1,024 seems about right. There are guides online that suggest you could go higher than this. I really haven't seen much of a benefit. It just seems to increase your overall I/O latency. Up next, physical devices. I really consider the choice of physical devices a sizing concern, so I didn't get too deep into it. If you watch Perry's presentation from yesterday, he'll talk about it in length. But just some general best practices. In general, go for local storage. You're going to have a much better time than any sort of networked or shared storage. If you are deploying SATA, go for at least 10K RPM SATA. 15K is even better. Alternatively, SSD is a great choice. If you can't afford to deploy SSD for everything, then I'd recommend that you take advantage of Couchbase's ability to segregate data storage from index storage and deploy your data on the SATA, deploy your indexes on the SSD. If you are using RAID, make sure, or any sort of storage controller, make sure that it's battery backed so you can take advantage of some of those file system mount options. And finally, make sure that your I/O is aligned from the file system down to the physical devices. This is a really complex topic. I'm not going to get into it here. There are plenty of guides online. Just search for how do I align my RAID I/O. And you'll have more data than you can handle on tips on how to do that. But make sure that you do. Unaligned I/O can result in a multiplier for the number of on-disk writes that any given logical write to your file system incurs. It's a bad thing. All right, 20 minutes, halfway there. Network tuning. I've segregated network tuning into its own section. This is sort of artificial. It's not really that separate from operating system tunings, except there is a big difference between all of the tunables we just looked at versus network tuning. And that is, you can tweak to your heart's content all of the previous tunings, and you're only going to affect the system that you tuned them on. Not the case with network tuning. If you get too aggressive with your network tuning, you can affect more than just your local server. You can affect the neighbors. You can even affect the switch, and you'll get nasty grams from your local network admin that you've induced buffer bloat or some other fun exotic issue. These settings, I'm not including any recommended hard numbers. These are things that you should really only change if you are experiencing either a network bottleneck, if you can demonstrate that you are seeing that, or if you are seeing drop packets or retransmits. At that point, get into these tunables. Otherwise, just sort of leave them alone. They're probably okay. Like everything else, we'll start with a basic diagram. These are essentially the layers that exist within the Linux network stack. So say we want to send some data across the network. The first place that's going to land is a transmission socket buffer. Below that, we have a transmission queue, otherwise known as a transmission backlog. Below that, we have a ring buffer. And then finally, we'll get to the NIC and transmit it over the network. So buffers on top of buffers on top of buffers. And at each layer, we can tweak these in order to make the network behave the way we want it to. The receive side is basically the same architecture, just in reverse. So if we want to improve the resilience of our network stack, there are a number of tunables we can look at. For buffers, so that topmost buffer that is closest to our application, we can set, well, these parameters. What these do is really set the initial buffer sizes for your transmit or receive buffers. These will get auto-tuned over time by the system to values that are more appropriate for your workload. But by setting better initial defaults, we can decrease the amount of time after a reboot that it takes for the network to get back to an optimal state. In general, all of these settings were defined back in 1993. All of them are generally not applicable to modern high-speed networks, and you can generally tune them up quite a bit. But I will leave it to you coordinating with your network admins as to what values make sense for your network. So a layer below the buffers are the backlogs or the queues. These really determine the number of packets or the number of connections that a system can queue up before you start dropping packets and forcing retransmits. What we can do here is generally increase these, again, quite a bit to allow many more packets or many more connections to backlog. And the next one, which is actually fairly new to me, but I'm pretty excited about, is receive packet steering. by default on a Linux kernel, all of the interrupts for the network are going to be handled by CPU 0. And if you have very fast CPUs, maybe that's not an issue. If you don't have very fast CPUs, for example, you're in a virtualized environment and you have CPU steal going on because some neighbor is stealing part of your CPU through the hypervisor, you could end up in a situation where you're artificially bottlenecking your network because you can't process all the packets fast enough because CPU 0 is just bogged down. What you can do is if you're seeing a very high system CPU percentage on CPU 0 that you aren't seeing on the other CPUs, something you can try is setting this echo F to the RPS CPUs parameter. And what that will do is allow all CPUs to take part in processing these interrupts, basically spread the load. And in virtualized environments, there have been a number of load tests to show that this, in particular, is very effective at improving your overall network throughput. The other thing, so we've covered resilience in the networking stack. Efficiency is the other topic. TCP in general is a very chatty, very noisy protocol. It's built that way because it's meant to go over lossy networks. Modern LANs aren't that lossy. They're actually very the opposite of lossy. And what we can do is cut down on the number of packets being sent over the network by adjusting some tunables. So we have TCP selective ACK that we can enable and TCP final ACK that we can disable. Essentially, these are just additional packets that need to be sent as part of the TCP protocol to make sure the data is arrived where we think it is in order to prevent too many retransmits. In general, pretty reliable networks these days. That's the opposite of the word I was looking for earlier. And we can safely enable these to reduce the number of packets on the network. We can also reduce connection overhead within our TCP IP stack. So TCP fin timeout, we can lower that in order to remove closed connections faster. And we can also enable TCP time wait reuse, which instead of having to construct a new connection from scratch every time we want to connect to a particular node, a particular endpoint, we can reuse any existing connections that might be in the time wait status, which can give you actually a pretty decent performance boost if you are churning connections often. And finally, these settings for auto-tuning are enabled by default on modern kernels. Doesn't hurt to check. So the TCP moderate receive buffer and the TCP window scaling, both of those should be enabled. If they're not, make sure they are. That will allow your TCP IP stack for the window buffers that we had discussed earlier to auto-adjust your workload to values that really make sense over time. And last topic on network is jumbo frames. This is hotly debated, particularly around network gurus, because in my opinion, it just means a lot more work for them. But for us, as consumers of the service, can make your network stack really much more efficient. So as an example, let's take a look at what it takes to send an 8 kilobyte object across the network. With the defaults of a 1500 byte MTU maximum transmission size, essentially maximum packet size, I would need to split this 8 kilobyte object up into 6 packets. Each of those packets has a certain amount of overhead associated with them. And of course, the process of splitting an object up into 6 different packets, sending them and then recombining them, that has some CPU overhead associated with it as well. A much better solution is to increase your MTU to 9,000. That is the default for jumbo frames, or the widely accepted default for jumbo frames. And when we do that, we can encapsulate the entire 8 kilobyte object into a single packet. We have 5 times less network overhead, and we'll make much more efficient use of our network bandwidth as well as our network processing. I've seen very good gains, especially on the higher end of objects. When you enable jumbo frames, I'd recommend that you at least give it a shot. Fight the good fight with your network admin. See if you can't convince them to enable this. It will need to be enabled across the entire network, so not only on your devices, but also on the switches. Give it a shot, can't hurt. To enable it on the Linux side, you can use ifconfig. So ifconfig Ethernet device, MTU 9000. And finally, I think I have about 10 minutes left, Couchbase tuning. Single most important parameter for tuning Couchbase is the amount of memory that you allocate to buckets. Pretty simple, I'm sure you've heard that a dozen times this week. Very important that if you are seeing a lot of disk I/O access, the best way to prevent disk I/O bottlenecks is simply allocate more memory and use disk less. Another important parameter here is if you have multiple workloads on your system and you want to be able to allocate your disk I/O resources differently between the workloads, take advantage of the new as of 3.0 disk I/O optimization, essentially disk priority settings for those buckets. So if you have any buckets that require higher disk I/O access and you want to ensure lower I/O latencies for those workloads, set those to a higher priority. Next is we can control how Couchbase manages your memory to an extent. So when you allocate a certain amount of memory to Couchbase, what we do is we try to use as much of that memory as possible for caching data in memory. If you have more data than you have memory, then Couchbase will have to at some point start ejecting data from memory so it just exists on disk. The point at which that occurs is controlled by a series of watermarks. So we have a high watermark and a low watermark. If you fill up your memory quota up to that high watermark level, then we have a pager that will go through and start ejecting data down to your low watermark. The memory above your high watermark, we're essentially reserving so that while we're ejecting data, you don't OOM the bucket by having writes come in faster than we can eject data. If you have a lot of memory allocated to a bucket, that default high watermark of 85% of your bucket quota could potentially be a very large amount of memory. And it could be the case where your use case can't write data into the system fast enough to really necessitate 15% of whatever huge amount of memory you've allocated. So it's, in that case, generally safe to raise your high watermark to, say, 90% or some other percentage that makes sense for your workload. And you can do that using the cb ep ctl command. Yes, very easy to say. That's in your opt Couchbase bin directory, and there's documentation on our website for exactly the command to issue to change those particular parameters. When it comes to views, a few things that you can do to tweak how the view system allocates your resources. The first is to understand how design documents and how views are processed. Each design document essentially is executed in its own thread, and as a write comes in, it'll be processed on that thread for all of the views contained within that design doc. If you don't have very many system resources, then consolidating your views into a single design doc will mean that you have just one thread running for view processing. It also means that you'll have just one copy of that data going through the view processor, so fewer memory resources, fewer concurrent disk I/O resources. If you are flush with resources and you want to improve the, lower the latency for processing these views, then what you can do is split your views up into multiple design documents. That means that you have now more threads running and you get greater concurrency on your view processing. Another set of settings that you can adjust are your automated index updates. So Couchbase isn't continually indexing your data as it comes in. What we do is we allow a certain amount of data to collect, and then every so often the indexer will wake up and then process that data, index it to disk. We do that because it's more efficient than running it through, running the indexer for every single write. But you are able to attenuate the rate at which that indexer wakes up in order to process data, and you can also change the minimum number of mutations that have to have accumulated before the indexer actually runs. So update interval is essentially the frequency with which the indexer wakes up, and then the update min changes, the number of changes that have accumulated. And you can change those values using the post command on the screen. Much more information about how this works on our website. XDCR, not sure if you guys can see that in the back. There are a number of parameters you can change in order to attenuate how XDCR functions. The only one that I really wanted to bring to your attention today is the max replications per bucket. Couchbase XDCR is actually a very efficient implementation. Sometimes it can be a little too efficient. If you have a low bandwidth connection between data centers, we can very easily saturate that connection. So something you can do if you're experiencing a saturated connection and you don't want that to be the case, you can tune down the number of replicators per bucket until so you're essentially throttling your replication connection. Alternatively, if you have just a wonderful 10 gig connection between data centers and you're not using all of it, you can bump that up a bit and better utilize your network. Compaction is a process that Couchbase goes through in order to clean up dead bytes on the system. Couchbase uses an append-only file structure, and every so often, in order to clean up dead bytes, we need to compact the on-disk data structures. And when this compaction runs, there's necessarily a disk I/O impact. Something you can do to attenuate when compaction runs is change the fragmentation threshold. A higher percentage on that fragmentation threshold will mean that the compaction runs less frequently. The trade-off there is you will incur more dead bytes on disk, so you'll have greater disk utilization until compaction runs again. If you have a workload that has peaks and valleys, essentially an off-peak period, say you have users accessing a website and it's mainly done between 10 a.m. and midnight. You have an off-peak period where you have very little activity. You can window your compaction to run during that off-peak period and not impact your production traffic by running during peak hours. And last thing before we get to questions, I see some Couchbase folks in the back cringing because I'm exposing this. There are some super secret settings in Couchbase that aren't immediately exposed in the web interface. They're not that super secret because we do have them documented on our website. But if you want to take a look at them, you need to add this query string to your web URL. When you do that, you'll get another link up in the upper right-hand corner of your interface that shows, that says edit internal settings, I believe, and you'll get this menu when you do that. I'm not going to go into all of these, but a couple that I want to make you aware of. The first is index-aware rebalance. In Couchbase, by default, we're going to try to keep your view indexes synchronized between the current node and the new node where you're transferring data during a rebalance. That process of keeping those in sync is rather expensive, and if you don't require that consistency between those indexes, you can disable that functionality and you'll actually get much faster rebalances in general. Another option is the max in-out, max in outgoing backfills per node during a rebalance. It's a very succinct title for that option. What that does is control the number of vBuckets that can concurrently be transferred between source and destination nodes during a rebalance. We default that to 1 because we want rebalance to be a background process and not impact your production workloads. But you can increase that if you have a lot of resources to send more vBuckets in parallel, and then you'll decrease your overall rebalance time. Whew. All right, a lot of stuff. Sure there are questions. I see one right there. Sure. Yep, so the tempo messages could be triggered a number of ways. Generally, the main way is if your disk write queue becomes sufficiently backlogged. If you exceed 1 million objects in the disk write queue, you'll start getting those tempo messages. That is true. There is another parameter. If you actually look in our documentation, the same place where we're talking about watermarks, you can raise that parameter as well. Other? Sure. The question is, what is a design document? A design document you can think of as just a container for views. It's a way to organize your views into essentially what we were talking about, how they're to be processed. So generally, you would put a bunch of related views into a single design document, and then all of those will be run within the same thread in order.
So when you said the fragmentation level for the compaction to run,
Yep.
is it better then to make it to set that lower because that has less fragmentation to the process versus higher? Because higher means that you will work harder, right?
Sure. So regardless of how much fragmentation you have, if compaction does run, then it will rewrite the full vBucket, right? So there is essentially a set amount of I/O that will occur regardless of how much fragmentation you have. The trade-off when you set it higher is you're just not doing that process more often. There is a secondary effect that your write latencies will also slightly increase because your binary trees will be that much longer. Something you should play with in testing. In general, you can increase it a bit just to defer the process, and you'll be okay. Another question? Can the access scanner be turned off? Yes, you can disable the access scanner. No idea. Sorry. The exact same section that talks about high water marks, there's another parameter for setting access scanner timings. And one of the timings is, I believe, a 0, which just means it never runs. Another question? Sorry, I could.
Google was talking yesterday that they disabled file system journaling.
Yep.
A lot more performance gain. They're recommending extended for XFS.
That's right.
Both of those are going to have journaling.
That's true. So I haven't played with disabling journaling in a long time. I don't know the effect of disabling journaling on Couchbase. I know that on ext3 it's totally true. You can get better performance. That is a trade-off, though, at boot time. How much, check disk, how long check disk is going to run if you have a hard power failure. I don't know the answer of what the effect would be. I would be wary of turning it off, though, to avoid long reboot times. I think that's all the time we have. I would like to encourage you guys, if you have our app, rate this session. It's going to be awesome, right? This is a fantastic session. Also, our beta is released, couchbase.com/beta. Give it a shot. Give us some feedback. That would be much appreciated. And if you want more in-depth operational information like what we just talked about, we do have operational training sessions in town near you. Training.couchbase.com. Give it a check. All right. Thanks, guys.